Linear regression is probably the most popular method for predicting variables. It's taught in stats, machine learning, and economics. But how does it actually work? In this video, I'll break down everything you need to know about linear regression, from the basics to the math behind it, and the key assumptions you need to keep in mind. Let's start with the definition. Linear regression is a statistical method used to model the relationship between one dependent variable and one or Wait, you've probably read that boring definition already. Maybe in a book or in ChatGPT. Bear with me and I'll break it down in a way that's super simple to grasp. Imagine you are a YouTube analyst and you want to predict how many views Mr. Beast's next video will get based on the amount of money he gives away. You collect data on Mr. Beast's previous videos, including the amount of money he gave away and the number of views each video received. This is how the data looks like in a plot. So, how do you make predictions? Well, all you have to do now is to draw a line through the data points. And now you can predict, for example, if Mr. Beast gives away $600,000, our model predicts 80 million views. But if he only gives away $100,000, the prediction is more like 10 million views. This is basically what linear regression does. It finds the line that best fits the shape of our data, so we can make predictions about new values. It's like having a crystal ball that helps us guess what might happen next. Well, we've talked about finding the best fitting line, but how do we actually do it? Let's dive into the math. Mathematically, a line is defined like this. This is the bias or intersection, which tells us the point where the line intersects with the y-axis. This is the slope, which measures how steep the line is. And this are the dependent and independent variables, the number of views and money in the previous example. And you might be wondering, if this is called simple linear regression, does that mean there's a more complex version? And the answer is yes. It's called multiple linear regression. Essentially, it's the same idea, but with more input variables and parameters. But don't worry, we're going to stick with the simple version for now, just to keep things easy to understand. Okay, back again with the question, how do we find the best fitting line? Remember how we can adjust the line by tweaking the bias and slope? Well, that's exactly what we need to do. We want to find the perfect combination of bias and slope that gives us the smallest error possible when making predictions. To do that, we use these formulas to iteratively update the parameters. Both are pretty much the same, so let's just break this one down, for example. So this is our current parameter, which we've initialized with a random value. This is the learning rate, which we'll get to in a bit. And this is the derivative of the loss function with respect to the slope. Let's dive a bit deeper into this term and see what's going on. A loss function is a way to measure how wrong your predictions are. Think of it like a game where you try to get your predictions as close to the target as possible. The loss function helps you keep score and improve your aim. We're going to use mean squared error, MSE, to measure our model's performance. Here's how it works. We take the difference between our predicted values and the true values, square those differences to punish the big mistakes, and then average them out to get the MSE. It's a simple but effective way to evaluate our model's accuracy. Now it's time to calculate the partial derivative of the loss function. Think of this as finding the steepest path to climb up the function, but since we're trying to minimize the loss, we actually want to go downhill. So we'll add a negative term to the derivative, which essentially flips the direction and points us downhill towards the minimum. Let's revisit the learning rate. Think of it as the step size that controls how quickly we move through the function. A small learning rate means we take tiny steps, like this. On the other hand, a large learning rate means we take giant leaps, like this. The magic happens when you repeat this process over and over again. With each iteration, you're refining your parameters, adjusting your line, and getting closer to the optimal solution. It's a gradual process, but eventually, you'll find the line that gives you the best predictions. And that's when the model starts to shine. By the way, this entire process we've been walking through is called gradient descent. If you look up the definition, you might see something like this, which is basically the same thing we've been doing, but using vectors. Notice that this term theta includes both of our parameters, and this gradient is made up of the partial derivatives we calculated earlier. Now that you've seen how linear regression works, it's time to talk about the fine print. The assumptions. I'm not going to overwhelm you with all the assumptions that come with linear regression, but I do want to highlight a few of the most critical ones. Let's start with linearity. This means that when the independent variable changes, the dependent variable changes proportionally. So, if your data follows a straight line, you're likely good to go. Just remember to double-check that the changes are proportional. Next up, we've got independence. This one's pretty simple. The errors or residuals of the model should be independent of each other. This means that the error associated with one observation should not be correlated with the error of any other observation. One way to detect a lack of independence is by examining a residual plot. If you notice a pattern, such as trends, cycles, or clustering, it suggests correlation between residuals, meaning the assumption of independence is not met. The third assumption is normalization. The error follows a normal distribution, meaning that if you make a distribution plot, it should look like a bell-shaped curve, where most of the errors should be close to zero. Last but not least, we've got homoscedasticity. Who gave it that name? Well, anyway, homoscedasticity says that the variance of the errors is constant, which means that the errors should maintain the same or almost the same along the data, just like this. On the other hand, if the errors get bigger or smaller as you move along the data, that's called heteroscedasticity. Seriously, who came up with these names? Here's a fun fact. If you take the first letter of each assumption, linearity, independence, normality, and homoscedasticity, also known as equal variance, you form the word line. It's a clever way to remember the assumptions for linear regression, since we're literally trying to find a line. Alright, it's time to finish the video. I hope you now have a solid grasp on linear regression. If this video helped you out, consider subscribing for more content like this. Thanks for watching, and I'll see you in the next one.